Welcome to The Explainer. Today, we're going to pull back the curtain on one of the most clever and, frankly, one of the most dangerous API vulnerabilities out there, server-side request forgery.
So let's just start with a chilling thought. Imagine an attacker doesn't have to bust down your digital front door. What if instead they could trick one of your own trusted servers, one that's already inside your secure network, into doing all their dirty work for them?
And look, this is not just some theoretical threat. A single vulnerability of this exact type, well, it was the key that unlocked the sensitive records of over 100 million customers in that massive Capital One data breach.
This vulnerability has a name, Server-Side Request Forgery, or SSRF for short, and the name really says it all. It's about forging a request from the server side, which effectively turns your own hardworking, trusted servers into unwitting spies.
It is so critical, in fact, that the Open Web Application Security Project, you know them, OWASP, they rank it as number 7 on their 2023 top 10 list for API security risks. So yeah, this isn't some obscure little bug, this is a top-tier threat.
So what makes SSRF so sneaky? It's all about how it completely sidesteps traditional security. You see, your firewalls, they're designed to block suspicious requests coming from the outside world. But what happens when the bad request actually comes from inside the network, from a server that's supposed to be there? Well, that's the genius of this attack. It weaponizes trust itself.
Okay, so how does this whole deception actually work on a technical level? I mean, how does an attacker really pull this off?
The vulnerability pops up anywhere an application takes a URL from a user and then has the server go fetch something from that URL. Think about functions like maybe generating a PDF from a web page or importing a profile picture from a link someone pastes in. If that user-supplied URL isn't checked, and I mean rigorously checked, an attacker can provide a malicious one. They can point it to internal admin panels or even use it to scan for open ports deep inside your private network.
The attack flow itself is almost deceptively simple, and it plays on this misplaced trust in just 4 steps. First, the attacker feeds the API an internal address, one they could never, ever reach from the outside. The server, not knowing any better, just dutifully makes the request, acting like a proxy. And then, boom, the internal service responds, and that sensitive information gets passed right back to the attacker.
And if you look at the official OWASP ratings, they confirm this is not some niche, difficult-to-pull-off attack. Its exploitation is rated as easy, its prevalence is common. So the barrier to entry for an attacker is low, but the potential technical impact is incredibly high. And believe me, nowhere is that impact more catastrophic than in modern cloud environments.
Okay, this is where SSRF goes from being just a problem to a full-blown catastrophe. Let's really dig into the most common and devastating target for these attacks, the cloud.
In pretty much any modern cloud environment, we're talking AWS, Azure, Google Cloud, there's a special internal service called the metadata service. You can kind of think of it as the server's own internal ID card. And it holds the keys to the kingdom, things like its temporary credentials and all its permissions.
This service lives at a really special, non-routable IP address. A lot of people call it the magic IP. It's only accessible from inside that server's own network. Well, guess what? An SSRF attack is the perfect tool to force a server to visit this internal-only address and steal its own secret credentials. This is exactly how the Capital One breach went down. The attacker found an SSRF flaw in a firewall, of all places. They used it to make the firewall request its own AWS credentials from that metadata service. Then, they used those super powerful stolen credentials to get in and download terabytes of customer data from storage.
The business impact was just immense. I mean, the costs from investigations, fines, settlements, it all added up to over $100 million. And that's not even counting the irreparable damage to customer trust. Okay, we've seen how dangerous this is. So, how do we actually defend against such a powerful attack? Let's talk about building our shield.
All right, the single most important defense, and I really can't stress this enough, is a strict allow list. This means your code should only permit connections to a pre-approved, explicit list of domains. That's it. The opposite approach, a denial list, where you try to block all the known bad things like localhost or 169.254.169.254, that is a losing battle, trust me. Attackers have countless ways to encode and obscure URLs to bypass those flimsy checks.
But one solution by itself is not enough.
you really need multiple layers of defense. This includes things like disabling redirects, so an attacker can't just bounce from an allowed domain to a forbidden one. In the cloud, it means using the modern versions of the metadata service, like AWS IMDS v2, which adds extra authentication. And at the network level, it means setting up firewall rules that prevent a web server from, say, talking to an internal database that has absolutely no business contacting.
This quote from OWASP just perfectly captures the mindset developers need to have. For decades, we've known you should never trust user input when you're building a database query, right? Well, we need to apply that exact same level of deep suspicion to any URL a user provides.
So after all this, what's the one crucial point we should all be taking away?
The big lesson here really marks a fundamental shift away from that old castle and moat security model. We just can't assume a request is safe because it's inside the walls anymore. This is the heart of a zero-trust architecture. Every single request, no matter where it comes from, has to be validated. We have to operate on a principle of verify, then trust.
So I'll just leave you with this one final question to think about. When a user gives a URL to your application, do you really know where your server is going? After seeing what's at stake here, that's a question worth answering. Thanks for watching.